Bom dia a todos e obrigado por se conectarem ao nosso webinar. Eu sou Luiz Vega, diretor de desenvolvimento de negócios da ANDRITZ Automation, e estou aqui hoje com o meu amigo Richard Van Vliet. Bom dia, Rick.
Bom dia, Vega.
Hoje o Rick vai falar um pouco sobre controles avançados na plataforma Metris. Para quem não conhece, a plataforma Metris é a plataforma de IoT da ANDRITZ que hospeda diversas ferramentas para gestão e otimização de processos e equipamentos. Essa plataforma une anos de conhecimento e modernas tecnologias que vem trazendo incríveis resultados para os nossos clientes. Antes de começar, deixa eu falar um pouquinho mais sobre o Rick. O Rick nasceu no Canadá e hoje vive na Geórgia, nos Estados Unidos. Ele é formado em engenharia química pela Universidade de Waterloo. Ele tem mestrado em cybersecurity pela Universidade do Grand Canyon. São quase 40 anos de experiência em processos e automação, com grande foco no desenvolvimento de controles avançados na indústria de papel e celulose. O Rick foi convidado para ser fellow da ISA em 2020. Ele já escreveu mais de 30 artigos sobre o tema e desenvolveu 4 patentes relacionadas a controles de processo para plantas de celulose. Rick. Ok. Bom, a sessão foi gravada e legendada para que todos possam acompanhar. Ela terá uma duração de quase 60 minutos e, ao final, teremos 15 minutos para responder dúvidas. Durante toda a apresentação, os microfones vão estar em mudo, mas vocês poderão enviar suas perguntas aí através do ícone, esse balãozinho com uma interrogação dentro que está dentro da plataforma. Após a sessão, vocês vão receber a gravação do webinar e uma breve pesquisa que vai sortear 3 power banks para aqueles que responderem. E também informações para entrar em contato com a nossa equipe de vendas. Dito isso, vamos à apresentação. Rick, it's up to you.
Thank you. Welcome, everyone. We will start the video now. The translations will be in the subtitles, and we'll join you back live for questions at the end. Thank you. Okay, for today's presentation, I'm going to start with a little bit of background on one of the major challenges that the industry is facing today. And that is not only is ensuring throughput and quality, but cost is becoming more and more a consideration in the global economy. Pulping economies or economics are concerned with producing the highest quality for the lowest cost. Capital expenditures are most often related to sustaining the business through maintenance versus growth opportunities. Some grades or product mixes can be involved. Pulping economics is a broad subject that ranges from day-to-day operations to decisions such as changing a grade mix to meet market conditions. Pulping economics directly interacts with many issues, and an emphasis is placed on making decisions driven by market forces, as well as the constraints of available fiber sources, global scheduling, and enterprise operations. The goal is to maximize production and quality, but also to maximize the profitability enterprise-wise. So what are the challenges? On the right, I'm shown our stylized mill manager and what keeps him or her up at night. Certainly environmental regulations are always a concern. Costs and profits, safety, reliability, people and training issues are a constant force. And of course, there are competitive measures. Regulatory control, which has been around for quite some time, are dedicated to maintaining preset targets. They don't have any knowledge of changing process conditions or any influence of constraints. There's no provisions for improving the process continuously, and that's where advanced process control, known as APCs, can enable a process in a real-time fashion. Inputs from both specialty sensors and other sources are becoming readily available, which enable autonomous operations. The overall goal is to transfer more and more tasks from operators to the automation system effectively. So what is advanced control? Control strategies designed to address a higher level management objective. These are centered around things like product quality, throughput, reducing the cost of euros or dollars per ton, reducing energy, and more assuredly comply with regulations such as environmental and all quality specifications. The bottom line here, it becomes a tool that can translate into a process control objective. APCs can be an enabler to autonomous operations because with utilization of advanced process control, there is less human involvement, especially in dangerous environments where sensors can lessen the dependency of humans going into the process. They're available 24/7. They can be used to react in a real time on disruptions, and the requirement for human experts on site every day decreases. Autonomous operations depend on remote operations, and they're able to handle increased system complexity. Basically, a need to have the ability to deal with changing conditions and less structured inputs. The graph on the right shows the traditional levels of control, starting with the process devices, the level 1 controls. These are often the single variable control, moving up into the level 3 or advanced regulatory control. Today, I'm going to speak of level 4 control, which is what we're calling advanced process control and optimizations. And as I mentioned, these have a foundation which enable autonomous operations. ANDRITZ solutions have the advantage of being totally integrated and aware of all process changes. The autonomous operations are enabled by the Metris UX system. So what's the difference between better control and optimization? When we look at control, quite often we consider poor control as a gap between a target and the process variable. As overemphasized on the left, where you have the oscillating process variable, good loop tuning and good control can show up as less variability and stabilized control. However, that's only improved control and not optimized control. The line at the top, as indicated by the specification limit, is where we want the process variable to spend more time closer. So making that change that's depicted on the right is allowing us to be closer to the operating limit in this case. So variability reduction in a broad sense enables economic benefits. In every process, there's usually a high side operating limit or a low side operating limit, such as if the customer wants to change chlorine dioxide greater than 20 kilos per ton, it will destroy the pulp viscosity. Another limit could be if kappa numbers get above 70, it'll plug up the screening system. And of course, in the slaker, if it gets above 100 degrees C, it can cause a boil over. So not only reducing the variability, but operating below but as close as possible to limits is very important. Process variability defines that gap between these operating limits, and statistics can be used to quantify this, such as an average process value plus 2 times the standard deviation defines the statistical limit at 95% confidence. Therefore, you can look at a process and determine how close it's operating to its limit. And there's usually a direct relationship between reducing variability and achieving results. So shown here on the left is traditional control, where you have some sort of spread of variability. The first benefit and requirement of advanced control is to first tighten up that reduction and cause a reduction in variability, and then in this case take a target shift to the right, which is closer to the capacity limit. This is a two-step procedure which we'll see several times. So what is a definition of advanced control? Advanced control is an enhancement of basic process control. It's not a replacement. It's aimed at delivering value to our customers through three main forces: throughput, quality, and now cost. APCs utilize a variety of technology to optimize the process in response to business drivers, utilizing minimum resources without compromising throughput, quality, and of course, target or cost targets. What are the objectives? Well, a controller, broadly speaking, is designed to address a higher level management objective, such as a corporate goal could be to improve product quality. And this starts by reducing the kappa number variability. The customer could want to increase throughput. They have more orders, and it is very expensive, although possible, to increase the throughput through a capacity increase with capital expenditures, but sometimes debottlenecking or shifting the variability of production can increase the overall throughput. Of course, as I've mentioned, reducing operating costs such as dollars per ton, reducing energy, and obviously reducing any environmental constraints. So with better control, you're going to have less upsets, better washing control, will use less fresh water, which puts less load on the environmental system. And obviously, number one is to create a safer process for the operators. So providing a control solution without properly defining the problem really is the wrong way to approach it. In order to apply a solution, understanding what the real problem is paramount. So what's the difference between control and optimization? Well, broadly defined, optimization can be a noun. It's the act of making the best or most effective use of a situation. It's a discipline of adjusting the process so as to optimize, and then using some sort of set of parameters without violating a constraint. In the case of cost, we are trying to minimize the cost, maximize the throughput. So I'm going to look at the pulping process here and focus in on the bleach plant. As we know, the bleach plant is an important process. After the fibers are separated, most of the lignin is removed, and we've recovered the liquor. It goes to the bleach plant for final purification and quality control. It's also a very high cost area. For example, a 1,000 ton per day mill, the cost of bleaching can exceed 19 million euros per year. So a modest 3% improvement in the application of bleaching chemicals could be worth over €500,000. So quite simply, starting with a loop, this is a front end of a bleach plant where you have a simple loop. We're applying chlorine dioxide, and at the very basics, we're ratioing it to the production. Therefore, we take the mass of pulp and the flow and concentration of chlorine dioxide. We could put it in a mass to mass or percent applied. So if an operator puts a target in, the regulatory system will maintain this loop to keep that percent applied dosage. Any influences, pressure compensation, variations in the flow, at some point will reach a limit that the valve is either 100% open or it's closed. But that's all that this loop does, is maintain the percent applied, and that's known as a regulatory loop. However, in the case of bleaching, similar to most other processes in pulping, it's actually a very highly interactive process. So even though we're applying over here the chlorine dioxide in a mass to mass basis of the flow, if there is a change in kappa, such as the kappa increases, then the brightness will drop unless there's a corresponding increase in the chlorine dioxide. If the production rate increases, even though the chlorine dioxide, which is ratioed to the production, will increase, the retention time in the towers will change and the reaction rates will change, and that too will have an impact on the brightness. So even though the entire process is set up with single loop regulatory controls, it is important and necessary to have a higher level strategy. So one of the possible solutions that's been identified and is very effective is termed MPC, or Model Predictive Control. This is a control technology that's been utilized for many years in other industries such as hydrocarbon processing. Today, it is being adopted and used in other industries such as cement processing, minerals, and of course, pulp and paper. It is a proven technology and it provides control solutions using constraints. It also takes advantages of feed-forward disturbances, sometimes measured, sometimes not measured, and it has the ability to utilize feedback. And it's designed, in the case of bleaching and other pulping processes, to handle delays and strong interacting loops. This makes it a perfect technology to utilize. On the paper side, our industry was quick to adapt it, primarily due to the availability of sensors and measurements. QCS systems are standard, CD and MD controls, and with the aid of a scanner, the economic benefit of having your paper machine or pulp dryer on control is well established. On the pulping side, however, it's been much slower due to a general lack of measurements, lots of connected yet not coordinated processes, and challenges with the connectivity to the underlying DCS. Many DCS systems traditionally did not have the horsepower in order to calculate some of the requirements of a model predictive control. And over the years, many attempts have been made with alternative technologies with positive results, but still not optimized results. The possibility of proven configurable tools versus programmable tools is now a reality, and the Metris UX system delivers that with its toolbox of proven APC solutions. As I mentioned, MPCs do have a history. They've been around in the process industry since the late 70s. There have been several examples of model predictive heuristic control, and then later dynamic matrix control. Modern predictive heuristic control was later called model algorithm control. DMC was presented back in 1979, and it has been widely adopted. The optimal inputs were computed as a solution to a least squares problem. Model predictive control has also been known as a constraint controller. So really, the objective here in the middle is a typical operating range, but there's a variety of factors that can keep the controller within that range. So operating at a set point is not necessarily a requirement. MPC strategies are used for stabilizing and maximizing throughput while satisfying all the process constraints. I'll show some other examples, but you can have a reaction that is allowed to give up some temperature, possibly with more retention time, and still operate within the sweet spot, which is known as the typical operating region. So really, what is model predictive control? Well, when it says model, so a model of the plant is needed to predict future behavior. And I'll go over in a moment how we can get that model. It is predictive in that the optimization is based on some predicted future plant evolution. So we have an understanding of the basic process, and then with some information that has been garnered, such as how the constraints interact, there is a cost function which allows the predicted output to be constantly compared to the set point or the target, and then over a horizon, see what type of change is required. At the heart of it, it's a mathematical model of the process that is used to predict future behaviors. Shown here quite simplistically, comparing MPC with the traditional PID or proportional integral control, the cars on the top track have no knowledge of each other. They're operating completely independent. They have no knowledge that the road is going to turn, and all they're trying to do is minimize their gap or their error between their target and where they actually are. So the green car is operating too slow, and the red car has gone around the corner, noticed a corner, and made too big of a change. So now he's way off track. And similarly, the car in front has moved too far to the left. So the PID only knows what's happened and adjusts the controller based on what happened and has no knowledge of what's coming. However, the MPC controller has a model of the process, and the control target is maintained with the knowledge of what's coming, and if the model is good enough, it will always maintain the target. However, models are never perfect, and we can utilize what's known in our world as a feed-forward disturbance, where we can say that it's raining out, so the road is getting slippery, perhaps slow down, and you are approaching a curve. So the point is, it also has the knowledge that there's other cars on the road. So again, knowledge is key, and all of this in an MPC strategy leads to a better tracking of the target. Okay, so getting back to an actual application, if we have a cascading loop that has something changing and we're going to send a feed forward signal such as a disturbance, the response as shown on the green was undershown, and then when a step change occurred, the response overcompensated and it took quite a while to get back to the target. Whereas on the bottom, when you have a model of what's coming, you can see that the disturbances were rejected very quickly. It stayed on target even when a big change was made. So that's a very simplistic view of how a MPC strategy has an inherent advantage over a PID when handling disturbances. Shown here, how does the MPC work in general? ANDRITZ is using a proprietary algorithm and has developed a MIMO or multiple in, multiple out controller. And what we have is a model has been created, and at each step, the controller computes the control signal to solve an open loop optimization. So even though we have a closed loop situation, we are predicting where the plant is going as opposed to where it is today. And then that predicted behavior, we can slice it up, known as the prediction horizon. And each scan, we are then looking at where we are in relative to where we've been, as well as where we're going. So this will show, I'll show later, this is very important. It's dynamic. It can handle changing conditions, and by looking at the receding control horizon, the control becomes tighter and tighter with time. Again, we have a reference signal here shown in green, and with an input or a stimulus, we know that the response to this input is going to cause some trajectory, and by slicing it up into different prediction horizons, we're able to change the response in a much more controlled, because now we have the past control action as well as the predicted future optimization. And depending on how you set the control horizon, you can converge to a solution very quickly, or what's known as the settling time of the process, you can combine it such that any production rate changes to a lime kiln, for example, do not cause the process to go unstable. So basically, there is an optimization within the MPC that's calculating control actions for the duration of the horizon. And the horizon is a adjustable parameter that can be set in the configuration. And what you're trying to do is minimize the cost function between the minimum and maximum production errors. So by tightening up the specification, the control actions are made to predict what's going to happen based on what has happening. So this is the key of having a model of the process and having knowledge of the background of where the process has gone as well as where it's going. So compared here with Unit 1, we can have a collection of the Level 1, Level 2, regulatory Level 3 controls, and it would be, like I said, every individual PID algorithm would have to be handled independently. Some sort of logic would have to be used to check constraints, and then finally through the DCS, you would put some intelligent set points. When you're using a model predictive controller, not only do you have the model of the individual process, in this case, it's taking up 2 of these controllers, but now we have what's known as local optimization. So the time, the DCS is operating every second. The MPC can operate fast, but it also can be slightly slower because it's going to take the past and future behavior. And now we have the ability of getting information from an even higher level, which is a plant-wide optimization. So if the production rate is changing at the digester, we will know eventually that production will go into the bleach plant, which not only requires us to adjust some of the conditions of the bleach plant, but we will need more chlorine dioxide. Conversely, from the washing operations, more liquor is going to be sent to the evaporators and then eventually to the recovery boiler. So we go from individual unit coordination to area coordination to mill-wide optimization. So benefits of an MPC is that dead time, which is one of the major constraints in the pulping industry due to the long reaction times, as well as the many inventory towers that separate processes. Dead times are very difficult to compensate for. There's been many attempts with such as a Smith predictor to try to compensate for variable dead time. But with an MPC, which is the basis of our APCs, dead time compensation is inherently built in. An MPC algorithm understands the cross-coupling, so it knows that different CVs and PVs are related, and the interactivity and the interaction of the variables are identified. Optimal control moves based on models of the plant, and most of the time it's easier to set up because it is configurable and easy to tune. Drawbacks are a model of the process is needed, and sometimes people are turning to first principles models, which can be used, and ANDRITZ has tools for that, but a more accurate, robust model can be done by real-time optimization and analyzing the process online. So some of the uncertainties that a first principles model cannot capture can be collected. It's easy to get lazy with MPCs and try to make gigantic MPCs. It's still good to think about how the process is operating and how we can minimize the complexity. What is the most important or low-hanging fruit that needs to be taken care of first? Many processes are nonlinear, and an MPC is based on a linear optimization, but what we do is in the range of operating targets, you can make a linear assumption. And of course, there are capabilities of using nonlinear controllers. But for most of the pulping processes, due to the relatively tight targets, it is possible to use the assumption that the process is linear. But how do you choose the proper solution? Going back to the bleaching example, there really is no one size fits all. Is there a reliable model of the process? Can you excite the process outside of the noise known as a step test or a bump test to try to glean information that will allow you to give the history of how the process dynamics? Digital twins can be used, including first principles models. However, do you have accurate instruments? Because in both cases, using a first principles model or doing a dynamic bump test, if accurate instrumentation is not available, it's very difficult to get proper information. Sensors or inline measurements, which are also continuous, are preferred. Although there are many analyzers on the market that are sampling systems, and they too can be used, understanding that they are discontinuous. And then of course, we have machine learning tools that can create soft sensors where measurements do not exist. As I mentioned before, knowing if the process is linear or nonlinear. Color development or brightness development overall is a nonlinear process, but in the regions that we're operating, we can make some very valid process linear assumptions. It is important to understand and identify inherent interactions, and some of those interactions, such as chip quality, may not be measured, but we know what the impact is. Like if the top separator amps start to go up, we can infer something is changing with the chip conditions. And then most importantly, are the dynamics well understood? So in oxygen delig, the kappa coming into the reactor is going to have a complete relationship to the discharge kappa if the amount of oxygen and alkali are not changed. So taking a look at the first two stages of the bleaching process as an example of building an APC, I've observed that even though there's two stages, they work in conjunction with each other. And even though they're in the bleach plant, brightness is not the primary control objective for these two stages. They can be referred to as an extended delignification stage because you must remove the remaining lignin before you start to brighten the pulp, because lignin that is bleached will not be stable, such as newsprint, which is lignin containing. When they brighten it, for example, with peroxide, and newsprint is exposed to the ultraviolet rays of the sun, the cover of the newspaper can revert and take on a brownish color. That is because the lignin was not removed, it was chemically altered. For most fine papers, copy paper, dissolving pulp, we want to completely remove the lignin. So in the case of those grades, the first two stages of the bleach plant can do that through the various oxidants, which are not limited to just chlorine dioxide. The EOP stage has peroxide and oxygen at its disposal, and the sum of all oxidants can be used in an APC strategy with knowledge of the incoming kappa and the target at the EOP washer to control this as one process, dynamically optimized to ensure that the degree of lignin delignification is kept constant at the lowest possible cost. So shown here is what's known as an expectation matrix. This is where the MPC starts to build. So if we move the amount of chlorine dioxide and we do a step change with chlorine dioxide, the residual will start to increase if everything else is held constant. After a delay, the pH will start to drop, and the measure of the lignin at the second washer will also drop. Conversely, if you step the chlorine dioxide, which is added after the D0 stage, there will not be a relationship because this has come after, but there will be a relationship between the E1 pH. So this exercise, known as the expectation matrix, can be done ahead of going to the plant. It can be done with the aid of an operator. The operator doesn't have to have any knowledge of models, Laplace, transforms, etc., but just a thought experiment of what relationships do you see in this process. And then once you are on site, then the next phase is called model identification. So again, cleaning up the data is very important. Some high pass filtering is used, but low pass filtering is very important. We need to think, is there measurement drift? In a short-term measurement, are we accurately reflecting changes? So basically, when you try to do closed loop identification, it's real important that you are identifying the model of the process dynamics and not the noise. So that's one of the problems. There's been a lot of work on closed loop identification, and that's also known as going back into a historical database and trying to find relationships. Quite often you can find those relationships, but as I mentioned before, the robustness of that model will be dependent on the amount of information that we gleaned. Did you excite the process sufficiently to get back information and just not process noise? This is a big concern in all of our units. So if we go to the next step and that we try to look at what are we trying to do. So we've clearly identified our control objective as the lignification control. We have an incoming kappa, which is the measure of lignin. We have the incoming kappa measurement. We have the production rate, which again is another source of error. We have to make sure that the pulp consistency is controlled as well as the stock flow, because all of the chemicals eventually are going to be updated based on a remote set point coming from the APC. So in this case, we have, as I showed earlier, the chlorine dioxide dosage control, which is the volumetric flow of chlorine dioxide solution times the concentration to give the mass of chlorine dioxide, and then divide it by the production rate or mass of fiber to deliver it in percent applied or kilos per ton, which is a very common regulatory control strategy that's ratioed only to production. Now we're going to give a remote set point that's based on not only the incoming kappa measurement, but what the resulting kappa is going to be 1 to 2 hours later. Now, it's also known that for each oxidant, which delignifies or cleaves the lignin molecule, it must be extracted with sodium hydroxide. So now we have what's known as we convert all chemicals to the same oxidizing power, and then we know what the caustic to TEC ratio is, and then we can do an intelligent sodium hydroxide remote set point. Okay, so once we've identified the process and identified the control strategy, if we turn to our Metris UX platform, it's shown here as the dashboard, and we select the application studio, we get into the application studio, and shown here on the right, we have a toolbox of all the APCs that exist as well as the building blocks to select which control we want to build. This can be done remotely as long as there's a remote connection to the DCS, because all of the values are brought in via an OPC link. This is kind of difficult to see, but this is the D-Link controller where it's a drag and drop, and then you just attach the various inputs, and on the right is shown the outputs. There's our D-Link controller, and then there's our total equivalent chlorine controller, which is being given the amount of oxidant used, and then this is coming up to give the dosages to the DCS. On the left is the actual block. So a compilation of all those individual blocks has been pre-configured into an APC block known as the D0 EOP delignification controller. It manages all chemicals dynamically. It's been fully tested. It's been optimized, and any cybersecurity risks, which are very common, code is a very common vulnerability if it's not done correctly. All of the ANDRITZ Metris UX blocks are certified that they have 0 defects, as well as there's a quality assurance certificate for every block. The objective is to manage all the chemicals dynamically, and it takes advantages of both feed forward, kappa, and feedback. So shown here again is the process overview, where you've got the kappa and the production rate, the D0 stage, the peroxide, the oxygen, and there's feedback. This is all handled now in an APC block known as the D-Link controller. Results are very important, of course. Shown here is a recent project that had 2 different bleaching lines, and the before and after case, we had a 3.2% improvement in the D0 CO2, but a 17% improvement in the peroxide. So in this case, and I'll describe this in a moment, we have minimized the use of chlorine dioxide by maximizing the amount of peroxide. From an economic standpoint, peroxide is often cheaper than chlorine dioxide, and therefore to get the same amount of bleaching, the APC in a real-time fashion has balanced the amount of chemicals. And this is a proprietary algorithm that we have that shifts the bleaching load as well as optimizes between oxygen, peroxide, and chlorine dioxide. Similarly, for the brown stock washing operation, where the degree of washing has to be balanced with the solids, we can optimize, in that case, what the dilution factor. The benefit of this control at this mill was about $14,000 a month, and it was very quick implementation. Another area of the mill that is well suited is in mechanical pulping as well, or TMP. Shown here is the process where we've identified the necessary inputs. We've segmented the control into a stabilization controller, which in the case of refiners is adjusting the plate position to maintain the energy used. And then with a quality feedback, in this case, freeness, a second controller is used to cascade set points, remote set points to the energy for the stabilization controller. Again, in the simple representation, we know that the feed screw is very important for motor load. If the dilution flow is changed, that will also affect the motor load. And if the feed screw is changed and the plate gap is adjusted, blowline consistency can change as well as pulp quality. So it's very difficult to control the refining process simply as a collection of single loops. An APC is required, and again, our MIMO controller is used. Here is an illustration of actual data. The production rate, a significant step change was done with the ACE controller on. You can see that the freeness is actually stabilized and the specific energy is moved to maintain the freeness target. So traditionally, if a production rate was made, the operator would have to attempt to move the plate position and keep his eye on the specific energy, all the while trying to maintain the freeness target. The controller kept the target with a standard deviation of 5.6 and a specific energy of 2.6. When the ACE was turned off, you can see that the freeness sometimes was outside of the limits. The standard deviation almost doubled, and the specific energy, in fact, did double. So here it's a multivariable control using a MIMO that allows for rejecting the disturbance of a production change and still maintaining the freeness target. I mentioned earlier, washing is another prime candidate for an APC. The washing process is extremely important as that is the crossroads where you're trying to send as clean as possible fiber to the bleach plant, but also by adding more water, you're going to dilute the liquor, which goes to the evaporation process. And the more steam you use in order to meet the recovery spec, which produces steam, you're going to be wasting money. So if you cut back on washing, yes, the solids will go up and the evaporator costs will go down. But if you underwash the pulp, the carryover of the dissolved lignin and the inorganic portion will directly consume chemicals. So what's needed here is an optimum set point called the dilution factor. These curves, this is the evaporating cost. As we increase the amount of water, we increase the dilution factor. Therefore, the cost of evaporation goes up. And as we increase the amount of water, the cost of bleaching is going to go down because it's nice clean pulp. So since we can't operate at an unlimited dilution factor, nor can we not wash the pulp because we need to recover the chemicals, an economic optimum is required. And we've developed a soft sensor called Online Dilution Factor Optimizer in the Metris UX environment, which reads the real-time bleaching costs as well as the evaporating costs, and then advises the washing APC of what the correct set point is. ANDRITZ, being a supplier of all of the equipment for a pulp and paper facility, we have developed APCs or advanced process control applications for every area. They are modular in format, however, they are also connected due to the coordination that is required. We can coordinate from a cost basis, we can coordinate from a production management, which is a huge opportunity. An APC can manage upstream and downstream disturbances such that if a maintenance outage is required in the bleach plant, we can adjust the fiber line and pulp dryer productions such that the downtime in the bleach plant is not disruptive. Those are real-time calculations where the APCs are managing both inventory levels as well as stock flows. On this chart, the various operations of a fiber line are shown on the top from cooking all the way to pulp drying. We have packages for all of these areas, and as indicated by the stars on the left, the main variables that are common in every single APC that we have developed is that we are trying to minimize process variations. That in itself is a combination of understanding that the valves are performing correctly. So we have an app called Control Performance Assessment. We have trending tools to show how the process is acting over time. We have a production management app which will coordinate production, and by stabilizing, we are going to minimize process variations. Maximizing the production is always a goal. We want to push fiber to the machine. We want to pull liquor to the recovery. And that requires not only inventory control within each unit operations, it also requires coordination from a global or mill-wide perspective. Of course, we're trying to minimize operator changes. So the number of changes that the operator needs to make can be substantially reduced. The fact that we have model predictive control can do a better job than an operator in anticipating dead times. The APCs can coordinate processes that can be several hours long, as well as understanding what the trajectory or the dynamics of the process is going to be. And then finally, we are trying to optimize the operational cost. Certain areas, such as bleaching, we might have to increase the use of one chemical, such as peroxide, but at the benefit of reducing a more expensive chemical. In oxygen delig, running at a constant percent delignification is fine, but setting the targets. What is the best combination of solids going to the recovery boiler and the cost to delignify in the bleach plant? So sometimes coordination over the whole mill is very important, and that's what an APC can deliver. So looking at the Metris platform, from a hierarchical standpoint, the level 0, known as the reliable mill, starts, as I showed earlier, with the field devices. A well-controlled mill, but not yet optimized, resides in level 1. Level 2 controls can be termed the optimized mill, where individual units are optimized, but still there's no unit-to-unit coordination. This is where the controls, the APCs that we've developed that meet the objectives of mill-wide optimization. And then finally, the highest level, the autonomous mill or the managed mill, is where we have not only a local mill visibility, but we have an enterprise visibility. And different business drivers can influence. Grade changes are handled by an APC. Recipes are very easily implemented. And if a mill wants to campaign between two different species, the APC configuration in our recipe handler is the perfect place. Now, to summarize, some keys to a successful APC project. You can't simply put new software or new technology on an uncontrolled process. It would be like putting a bow tie on a bum. You are spiffing up some of the appearance, but really not doing a complete job. One of the first things that we do, rather than trying to sell a product such as an APC, which is a product, we want to sell a solution. And you need to know what the problem is. The best and most effective way of determining the product, the true problem, is to perform an audit, and this starts with variability identification. We're able to identify not only the capability of your process, but we can compare it to other processes on the basis of coefficient of variability. Doesn't matter if the targets are different, we have a benchmarking tool which shows what the variability should be on a well-controlled process. which leads us into step 2. It's imperative that you tune and optimize the regulatory loops. Excuse me. We will be updating remote set points for things like temperature and dosage and fuel, but ultimately those set points are going to be delivered by a regulatory loop. If the valve is not performing or the regulatory controller is not properly tuned, the APC will not be able to handle all of the disturbances. It's also important to have a very efficient integration between the DCS and your application, in this case Metris UX, in order to ensure the ability to monitor the APC applications. You need the same general set of displays. This cuts down on training. It's been said that the APC is too complicated, so we combat that by making the look and feel of an APC dashboard very similar to what the regulatory dashboards would be. This visibility aids in decision making and leads to better operator effectiveness. So once you begin to design an APC and you understand the problem that you're trying to solve, it's important that you perform adequate step tests or bump tests to really understand the process dynamics. This is known as the model ID phase. And then it's key to identify the key KPIs. How do you know that you are successful? What control objective have you met? Is it dollars per ton? Is it quality? Is it a production increase? Making a tank level that has some variability and it looks flat might not meet the control objective, because if a production increase is supposed to be buffered by an inventory tank, then perhaps the level shouldn't be set to a static target. And having the level in an inventory tank move is really the proper use of an inventory tank. So the real KPI in that case was rejection of any process change, production change disturbances to maintain, say, the brightness. Now, the objective of the third step is to design and implement the APC application. And the goal here is agility and to configure versus program. So dividing into these 3 steps is very important. Tuning the regulatory loops, step testing and model identification, and then finally choosing the correct KPI. By using the Metris toolbox of APCs, this cuts down on the financial impact of having to develop, customize one-off controls that may or may not be supportable. And the most important criteria, which is what we are trying to develop from day one, is the trust and confidence in the advantage of an APC strategy. Why are we doing this? For some, it could be a reduction in manpower, but that's a short-term goal. The long-term goal of implementing APC strategies are to remain competitive and keep the salability of the product at the highest possible quality. In order for this to be successful, gaining the trust and the confidence is an absolute must. And finally, benefits of a Metris APC solution is that building APC strategies from scratch can be very expensive. Detailed modeling is very expensive and often does not capture all of the dynamics. Using a Metris UX proven APC solution, it can speed up implementation time from a matter of months versus up to 12 months. The benefits are sustainable and much easier to maintain. Less than 5 to 10% of an engineer's time to maintain is needed afterwards. Online availability typically is greater than 95%. And as I mentioned, an integrated HMI makes the training time much shorter. Remote monitoring today is a reality and almost a necessity. Remote monitoring enhances the ability to maintain and certainly defines a higher ROI. So Bottom line is delivered through the Metris UX system. ANDRITZ's APCs improve profitability by maximizing throughput, minimizing quality variations, and minimizing cost. With that, I will take some questions now. Thank you.
Bom, teve um pequeno corte aí na finalização, mas a gente pode seguir para a sessão de perguntas e respostas. Para quem estava em dúvida aí, pode enviar as perguntas tanto em português como em inglês, que eu vou fazer o papel aqui de traduzir para o Rick. Espero que tenham aproveitado aí a sessão. So Rick, let's start the question and answer session, okay?
Okay.
A primeira pergunta que eu tenho aqui é relacionada a Digital Twin. Muito tem se falado sobre Digital Twin recentemente. Será que essa tecnologia vai substituir os APCs? So, Rick, we are reading a lot about Digital Twin technologies. And what do you think? Could this technology be a replacement for APCs?
No, that's a very good question. Digital twins do deliver a good first principles model of the process, so they can be used to supplement an APC strategy, but by no means would a digital twin be a replacement. As I mentioned in the seminar, the capturing of the actual dynamics of the process, so it's never achievable to get a perfect model, but a digital twin, which is based on first principles, can get you most of the way there. So equipment capacities or overcapacity, those differences are captured when you do online model identification. So to summarize, a digital twin can operate in the background, but the preferred method of real-time optimization is to use real-time data through such as a model predictive control.
Ok, good. A próxima pergunta aqui é: o que é MIMO? So, Rick, what is MIMO? What MIMO means?
MIMO means multiple input, multiple output. So quite simply, a PID is a single input, single output. So when we describe a process, yes, there is a flow controller. Yes, there is a temperature controller. But when you put that together, the entire process is described as a MIMO, multiple in, multiple out. We can also have multiple ins, single out. That's known as a MISO. So when we consider an APC for an entire process, that's why we look at all the interactions, and it results in a multiple in, multiple output, highly interactive strategy.
Ok, caso não tenha ficado claro, eu vi que deu alguma confundida ali na tradução. Então, MIMO é multiple in, multiple output, múltiplas entradas e múltiplas saídas, né? diferente de um P&D, que é uma entrada e uma saída. A próxima pergunta você usa MPC com um setpoint não alcançável como estratégia para minimizar o custo de químicos no branqueamento. So Rick, do you use MPC with unreachable setpoint strategy for minimizing the chemicals cost in bleaching?
If I understand the question correctly, we will set constraints. So as I mentioned, another term for an MPC is a constraint controller. So we do try to avoid saturation. Obviously, brightness is a prime example. If you over apply chemicals, the variability will go down because you've saturated the brightness. If we add a constraint, it can be in two levels. We can have a constraint of kilos per ton of an individual chemical, and then we can have a constraint for cost. So if we have a total cost constraint that's weighted, most importantly, then we will reach a constraint. For example, oxygen, which typically is the cheapest chemical, and then we will try to reach the constraint for peroxide and make the most expensive chemical. So I don't know if that completely answers the question, but again, it's all based on constraints and priorities, which is a weighting function.
Ok, caso não tenha ficado claro, pode enviar novamente aí mais algum comentário ou pergunta. A próxima pergunta aqui, você falou sobre os bump testes para identificar o modelo, requeridos para identificar o modelo do processo. Isso vai causar uma produção fora de qualidade ou um distúrbio de processo? So, Rick, you mentioned that bump test or step test is required to identify the process model. Will these cause off-grade or upset the process?
No, great question. As I mentioned, what's important is that we are identifying the true dynamics of the process. So you're not going to make very large steps, and due to the retention time, say, of a digester or a bleaching stage, we don't need to make a bump test or a step test that lasts for the whole duration. So a small perturbation to the variable we're identifying, it could last, as little as 10 minutes. We could do a series of steps. We could go up 2 steps and then down 2 steps and then back to normal. So in the end, absolutely not. We're not going to be allowed to create off-grade, but the key is making sure that the perturbation is above the noise of the signal. And closed loop identification from historical data certainly is possible, but it's not preferred. Online step testing is the best, most effective, and it can be limited, once again, to minimize any disturbance.
Ok. Para modelos preditivos, para MPCs, é necessário identificar se os loops são abertos, se é uma malha aberta ou uma malha fechada? So, Rick, for model predictive control, is closed or open loop identification necessary?
Well, the key is that a model of the process is necessary. As I mentioned, first principles models can get you partway there, but in order to capture the true dynamics, because again, in any controller, the feed forward portion, the more accurate the feed forward portion is, and again, with the long dead times in pulping, we're always going to utilize feedback, but the better the feed forward is, the better the control would be, and the better the process model, the better the feed forward will be. Therefore, as I mentioned earlier, open loop identification is preferred. There are techniques being developed to use closed loop yet online identification. So actually when the controller's running, we can be identifying a model in the background and then use the performance characteristic. So the key is that we need to have a good, robust model.
Great. Uma próxima pergunta aqui. Você tem algum MPC no branqueamento operando para controlar a razão de químicos? Tem isso em alguma planta? Onde? So, Rick, do you have the bleaching MPC running and controlling the chemicals ratio in any mill, and where?
Yes, we have a project running in Indonesia. We have a couple of running in Canada on the Metris platform. Of course, we've added some new technology that comes with the Metris UX platform, but ANDRITZ has a long list of bleaching projects that we've done over the years. The difference now is that we're able to do the optimization using all of the other tools of the Metris platform. This starts, again, like I mentioned, with our deep understanding of the process. As an equipment supplier, we're able to add certain things. And of course, the choosing of reliable sensors is key to the strategy. But yes, we have another project commissioning this summer, and we're getting several examples using the new MPC strategy.
Ok. A próxima pergunta: com que frequência precisa atualizar o modelo? Tem algum período para fazer o update, para atualizar isso? So, Rick, how often do you update the model? Is there any period to update it?
Yes. So basically, you know, the old adage is software doesn't break, but if the controller is not performing, it usually means that the model is no longer representative of the process. So we have a control objective that we're trying to achieve. And as I mentioned, the feed forward portion is quite important. If the reliance on feedback becomes greater, that usually means that you are under or overdosing because the model is starting to degrade. Therefore, we have a parameter that monitors when a new model is required. So we have another block called sensor correction, for example. On a very simple basis, we're doing a online comparison to a lab sample and a measurement. As that R squared starts to deteriorate, it tells us if a recalibration is required as opposed to a bias adjustment. Similar concept when you're doing an MPC strategy is as the model stops representing the process, we have a parameter which indicates perhaps a new model is required.
Ok, thanks, Rick. Bom, tem mais algumas perguntas aqui, mas a gente não quer extrapolar o tempo, então as perguntas adicionais serão respondidas depois por e-mail. Espero que tenham todos aproveitado a sessão e em seguida vocês vão receber o vídeo e os nossos contatos aí. Não esqueçam de preencher a pesquisa, isso nos ajuda bastante. So Rick, we just finished here, and if you want to say your last words and thank the audience.
Okay, yes. Muito obrigado. Thank you very much for joining and interest in the ANDRITZ MPCs. I could be contacted if you have any specific questions. And once again, thank you everyone for joining.
Thank you, Rick. Obrigado a todos.